Hello, and welcome to Integrating Digital Accessibility in the Chemical Sciences and Supporting Visually Impaired Students. We will look at an overview of disability and inclusion, why we need good practice, bespoke support for visually impaired students, and the impact of training staff and students on good practices. Disability is defined as one of the protected characteristics under the Equality Act 2010. Approximately 1 in 5 people are estimated to have a disability in the UK. A definition of a disability is some type of impairment which, in interaction with various barriers, may hinder full and effective participation in society on an equal basis with others. There is much data to support the fact that people with disabilities are not fully included in society. For example, employment data shows that disabled people are almost 30% less likely to be employed than non-disabled people. Approximately 17% of students who enter higher education declare a disability, and this drops to 13% for the physical sciences and down to 9% in the chemical sciences alone. Different types of disabilities have different impacts. For example, when considering severely visually impaired students, there is evidence that they are greatly underrepresented in the higher education sector. And the impact on people with visual impairments is that they are highly unlikely to be able to hold down long-term jobs or form meaningful relationships. There are many conditions that can lead to visual impairments, which is why a range of good practices are required to reduce barriers. And it turns out that in reducing barriers for people with visual impairments, we actually can reduce barriers for people with different or no conditions. So when we talk about creating barriers, what do we mean? This slide has an image which is a scan from a book. The color contrast is poor, the font size is small, the resolution is low, and it's very difficult to actually read the image and the information in the image, and it's completely inaccessible to an optical reader, so it's digitally inaccessible. If instead universal design good practices are used when creating documents, this will remove many of the barriers at source, although individual adaptations may still be required. Good practice regulations are embodied in the Web Content Accessibility Guidelines, which are internationally recognised. The guidelines are extensive, however, from the point of view of a higher education practitioner, there are relatively few types of documents that we need to focus upon, such as PowerPoint for presentations. From the guidelines, we can distill a set of instructions which, if put into practice, will create documents which are digitally accessible. We can show people how to use accessibility checkers and how to solve issues that may arise, such as missing alternative text, how to add the text and what it needs to include, or how to improve the navigability of a document. At Kent, we use an additional accessibility checker called Blackboard Ally, which picks up issues not picked up by inbuilt software, accessibility checkers, for example color contrast, and will grade a document with an accessibility score as a percentage. In order to change the culture of an organisation to be more inclusive, you have to train the staff, and the best way of doing that is to provide dedicated training sessions and back this up with a repository of good practice instructions and additionally training videos and materials. At Kent, since beginning training, we have seen over a 3-year period an improvement of 50% to 80% of the average score from the Blackboard Ally checker with respect to accessibility for teaching material deposited on our intranet, and we use Moodle. And this is despite a huge increase in the volume of teaching material that has been uploaded. In the physical sciences, this figure was slightly lower, at 74%, and that's because the physical sciences has challenges in representing alternative text for chemical structures and mathematical equations. All activities should embody these values, for example when hosting a conference, and the feedback that we have had has always been very positive, both from disabled and non-disabled people. Coming back to the chemical sciences, I said earlier that sometimes individual or bespoke solutions may be required. This image shows laboratory adaptations whereby a webcam was used to capture a reaction flask. The reaction flask was displayed on a screen, and the student with severe visual impairment could get as close as they needed to that screen safely and use what residual vision they had to follow that reaction. A webcam can also be used to magnify laboratory equipment readings, for example in this case a weighing scale. And if this is combined with the availability of laboratory manual or pro forma which has been prepared using digital accessible universal design criteria, this will enable the student to engage very effectively in the work that's been set to them. When preparing training videos for students, one should recall that not everything can be seen by all students, and actually describe the equipment that is present and what is happening and the manipulations. If videos are already prepared, then one can consider adding audio descriptions to those videos. Although bespoke solutions can be time consuming, they're very much appreciated by the individuals involved and can have some unforeseen benefits. For example, faculty learning technologists to emphasise how much they informed our transition to online teaching for all students during the COVID pandemic. Changing the culture to be more inclusive also involves training the next generation. In this study, 3 separate cohorts of finalist students who had to give a presentation were given advanced training on how to include universal design practices relating to PowerPoint. The training was given in person, and significantly there was no requirement from the students to include these good practices in their presentation, and there were no marks associated. Universal design criteria that don't require a huge amount of additional time, such as navigability of the document, using large font and ensuring good colour contrast in the imagery used, were readily adopted by the majority of students. Alternative text, which however does require more thought and time to implement correctly, was only adopted by 13% of students. In this slide we have an example from a student who also adopted alternative text, and all the slides were made available to all the students, and in fact the alternative text for the graph shown in this image does actually help to highlight what the student wanted to present. And this highlights that using alternative text and making the slides available beforehand is a benefit to all users, not just people with visual impairments. We can see good aesthetic values, good size font, and a range of imagery including chemical structure were used. Overall, 71 out of 72 students engaged with at least one aspect of universal design. In comparison, when looking at data from previous cohorts, that figure was less than 1 in 20. When looking at Blackboard Ally scores, without training, only 13% of students prepared presentations which had reasonable accessibility scores, whereas with training this increased to 82%. This was reflected in feedback from the students who in the main hadn't heard of digital accessibility good practices, but were very grateful for that knowledge and were very pleased to take it into the workplace. The proactive inclusivity approach adopted by Kent has been recognised on a national level by a white paper co-authored by Lord Blunkett and also by a Times Higher Education National Award. And before I finish, a call to arms. If you have resources which have been prepared using universal design criteria, please consider making them freely available. And if there is a takeaway message, is that yes, good practice will help eliminate barriers for people with various conditions, but overall good practice actually benefits all of us. I would like to thank the Royal Society of Chemistry for the EDI Award 2020 and also a huge thanks to the students and colleagues at Kent who have supported this work over the many years.